Hello, calculus scholars. Oh man, this is just quite a week that never ends. Um, Mrs. Benzel is still sick with the flu, and I want to just teach you guys. So we're just going to go ahead and do that today. Anyways, I want to clean up and make sure we're on the same page about section 4.4. What our plan is for the next 2 days and next week. We're going to have some review stations over integrals tomorrow. And I definitely will be in tomorrow because Alice has, daycare that day and they're open. And we'll have some time to get used to the types of integral questions that I ask on the benchmark. We get practice over that. You're also going to get your study guides today from the benchmarks. And question 14 through 19 on the study guide should more or less prepare you for the mastery assessment that we're going to have, which will have definite integrals, property of integrals. So I'd like to be able to, kind of clean that up and take questions from that before our station work on Friday. All right, section 4.4. So these are properties of integrals. And these are kind of, some useful properties that we kind of see on the type of questions that we're about to go through. The first property is that if you have an integral that has the same upper and lower limit, then that integral is 0. The second property here says that if we have a value c that's between a and b, so like let's say we had an integral that was between 1 and 3. Now if we took the integral of like 1 to 2 and then the integral from 2 to 3 in x value, and we added those, that would have the same effect as going from 1 to 3. So kind of, has a little bit similar logic to something like, let's say, the segment addition postulate in geometry. Another thing that you may notice about some homework assignments is you may have an integral sometimes where the upper limit is on the bottom and the lower limit is on the top. But one useful property that we have with integrals is that if you put a negative sign in front of the integral, then you can flip the limits of integration. So that way you can kind of have, your conventional upper limit on the top and lower limit on the bottom. Another property that we commonly use, if we have a constant before a function in an integral, if you take out the k, the constant, and then just multiply it by the integral. We can also, of course, and we kind of do this all the time when we have polynomial functions, we just kind of like take the integral out at once, but you could like just separate them into separate integrals. So if I had a function called f and a function of g, if I added or subtracted them, it would be the same effect. Even functions like parabolas, my textbook parabola is, the typical token child of the even function. It's nice and symmetrical. So if you have, the positive and negative version of your upper and lower limits, like let's say 2 to -2 or -3 to 3, you could have the same effect where if you go from 0 to the upper limit, just in the positive world and multiply it by 2, it would be the same effect. And then on odd functions, things like our typical cubic or a linear function, we see that when we have the symmetrical, negative a to a, that the value is 0. So our typical test question in section 4.4 involves looking at integrals. And I give you integrals that we know. So like the integral of this function f from 0 to 3 is 6. And from 3 to 7 is -8. And our goal is to get everything in terms of integrals that we already know. So like on this first one, Well, I know the integral from 0 to 3, this is the integral from 3 to 0. But fortunately, there's a property that says that if I put a negative sign, I can flip the limits of integration, not limits of immigration, limits of integration. So I could look at, something like number 3, this property 3, and I could just flip the limits of integration and put a negative sign in front. So that way, I know that the integral from 0 to 3 of f of x is 6. I just put a negative sign. And I kind of like, I'll have like kind of a menu of properties, and I like to kind of cite what property I used. That way, if there's any flaw in the logic on the test, I can kind of record the properties. Now this one, I have the integral from 0 to 7. Well, here's the good news. I know the integral of 0 to 3. I also know the integral from 3 to 7. So I'm just going to divide it into those two integrals, like taking the area under the curve from 0 to 3 and then the area from 3 to 7. And guess what? I'm provided with those. So 6 plus negative 8 equals to negative 2. This is kind of like the duh property of integrals. You know how guys like reflexive property. But the integral from 3 to itself is 0. This one, well, I do have to do a little flippage to get that upper limit on top and pull that 3 out. And I kind of divided it into 2 steps. But after that, I get negative 3. And then the integral from 3 to 7 is negative 8. And that gets me a positive 24. This one, I got the integral from 3 to 7 of 2 plus 3 f of x dx. So I'm just going to kind of divide it into 2 pieces. Now this integral, is a really easy definite integral where it's just, 2x. And I just kind of evaluate it just like the old, definite integral unit. This one, I am provided with this 3 f of x. I pull the 3 out. And, as a result, I get negative 8. If I'm having an even function of negative 3 to 3, this is same as saying twice of 0 to 3 of f of x dx. That's 2 times 6 to give me a total of 12. And last but not least, integral of an odd function. Well, if it's an odd function and there's symmetrical limits of integration, from negative 3 to 3, then of course that is equal to 0. Another type of problem that I like to give, and we'll have a little bit of station work with this type of problem, is this area under a curve. And it's kind of like the Riemann sum problems, except now I kind of am taking them into, familiar geometric shapes. So you could see, I kind of like pieced this. So I did a rectangle that was an area of 2, another rectangle that was an area of 2. This is a quarter of a circle with a radius of 2. That comes out to pi. That's symmetrical, so that's also pi. Positive 1/2, negative 1/2. And I can actually look at the integration regions and I kind of capture what I'm adding. And if you're just showing me, kind of like in a Riemann sum, what you're adding, I'm okay if you go to your calculator and turn them into decimals. So this one would be like 2 plus 3.14 plus 1/2. So you get 5.64. Now, if I'm going from 0 to 4, then I'm going to include the 0 to 3. So that 5.64 figure, and then I'm just going to subtract 0.5. And things are really nice when I'm kind of doing the symmetrical negative 3 to 3. Well, I know already that 0 to 3 is 5.64. And this is symmetrical about the y-axis. So I'm just using symmetry and multiplying it by 2. So, if there's symmetry, just multiply by 2, and you'll be able to get the answer pretty well.